Can you go to the picture for a second? Can we discuss this?
We can.
What does it look like to you now? Go all the way up. I want to see the top of that dress.
Back in 2015, the phrase breaking the internet was still new, and something broke it hard.
That darn dress, you know the one I'm talking about, it's been inescapable today, dividing the world between those who see white and gold and those who see blue and black. So tonight, we went in search of answers. When you can't believe your eyes, what can you believe?
Even today, if you showed this photo to a group of 3 or more people, I guarantee a fight will break out. That's what happened to us just a month ago.
Okay, wow. Scam. Look at the size of the screen.
I'm looking at it.
Look at the lace. The little lace detailing you can see is black.
No.
Whoa. Sarah, what are you saying? Sarah, where do you come down on this?
I want to go and get a crayon. Like a crayon that's called like camel or one of those brownish beige colors. That is the color of this dress.
You're wrong.
Was this upsetting? Yes. Did it disrupt our sense of reality so much that we had to get to the bottom of it? Absolutely. We're a history of science podcast, so we don't really do well with leaving a bunch of unanswered questions on the table. For example, if Mariel saw white and gold, or beige as she insisted, and I could only see blue and black, then what the heck else were we not seeing the same? Do we even exist in the same reality? And while I'm tempted to say that the real issue here is that there's something wrong with Mariel and Sarah, I'm gonna go out on a limb and say it's bigger than that. Color has a seriously fraught history. The question of whether we're truly seeing things differently or just seeing the same thing and describing it differently, it's bothered people for a long time, and for good reason. We treat color like it's a clear measure of whether or not our brains are working the same. And so when we start talking about something we've deemed basic, what color is this? We expect an answer we can all agree on. Only some colors elude us. In fact, it's fitting that the actual color of the dress that broke the internet was blue. Because of all the colors, blue seems to escape pinning down over and over again. It's so famously difficult that we have a name for it: fugitive. Blue is a fugitive color. But how? And why? And what does that even mean? From the Science History Institute, I'm Alexis Pedrick, and this is Distillations. Chapter 1: The Wine Dark Sea. Kai Kupferschmidt is a Berlin-based science journalist who spent years covering everything under the science sun, from infectious diseases to psychology to climate change.
And one of the topics that just kept coming up again and again, like in this weird way, was the color blue, like in very different contexts. If there was a color that was somehow interesting or complicated to make, or it wasn't clear what its function was in an animal, it was always blue. And so when an agent came up to me at some point and asked me if I had any book ideas, I was like, honestly, what I really want to do is to figure out what the hell is going on with blue.
When Kai finally wrote this book, Blue, In Search of Nature's Rarest Color, he stumbled upon the story of William Gladstone, a 19th century British politician.
He was prime minister, I think, 4 times in his life. But he was also this huge fan of the Greek poet Homer. And so at one point in his life, he wrote this huge tome of a book. It's like 1,700 pages. And it's called Studies on Homer and the Homeric Age. And one of the things he looks at is how Homer uses language around color. How does he actually describe things? And he was the first one to really notice that if you do that, there are some really weird things going on. There's very few color terms, and when there are color terms, they're sometimes a little bit unusual. And one of the things that he points out is that the word blue never appears anywhere. Gladstone writes at one point, like, you have this beautiful Greek sky, you have the sea, like literally if you go there, it's blue all around, and yet the word never appears.
Homer describes a lot of things as black and white, fewer things as red, and even fewer as yellow. But importantly, he doesn't describe anything as blue. In fact, he famously calls the ocean the wine-dark sea.
So the explanation that he comes up with is this idea that maybe they just couldn't perceive it, because to him it felt like if you had been able to see the blue, there's no way you would have gotten around actually writing about it. And so he thinks, well, maybe there is just nothing there for them. And so that's where this idea creeps in that, okay, something must have happened between the age of the ancient Greeks, where they didn't see this blue, and what was then, the Victorian age of modern humans, and their kind of perception of blue. And this is where it ties into a lot of, racist ideas that were very common at the time of, oh, okay, there is development in humans that's kind of like a gradual process of almost evolution, of developing higher faculties.
And maybe color vision was one of those things. Maybe only the people living in England in the Victorian age had developed the ability to see the full spectrum of colors. Even Charles Darwin himself wrestled with vision when he was thinking about evolution.
Nothing troubled Darwin more than that about the origin of the eye.
The belief that an organ so perfect as the eye could have been formed by natural selection is enough to stagger anyone.
The earthworm has a layer of light-sensitive cells in its skin that can detect light from dark. It's the simplest eye possible, and all that an earthworm needs. If a random variation should cause these cells to be set back in a pit, then the animal can detect the direction of light. Darwin argued that there were no limits to what such a process might ultimately produce.
A structure even as perfect as an eagle's eye might thus be formed.
And speaking of Darwin, he's the one we usually think of when we hear the word evolution. But in the 19th century, there were plenty of theories floating around, including one from French zoologist Jean-Baptiste Lamarck. The classic example of Lamarckian inheritance involves a giraffe stretching its neck to reach the leaves at the top of a tree. Over time, by sheer will, its neck gets longer, and then it passes that trait on to its offspring.
And so, for a lot of people at that time, they thought of evolution as basically this gradual improvement from generation to generation, but in terms of traits that are acquired in the lifetime of one individual and then passed on to the next generation.
This is what Gladstone was thinking about while writing about the evolution of color perception, and his provocative idea inspired German philologist Lazarus Giger. A philologist studies the history of language by looking at literature, and Giger studied the classics, as in the Bible, which has no mention of blue, and the Rig Veda, Hinduism's oldest sacred text, also no blue, despite a huge number of references to the sky. Giger's ideas about evolution built off of Gladstone's and got further developed by an ophthalmologist named Hugo Magnus. They believed the eye needed to be trained over generations to see color.
The innermost layer of the eyeball is the retina. The retina is actually a part of the optic nerve which transmits the light impulses to our brain. The retina is the most important and complex structure in the eyeball.
So their idea was that over time, as the light strikes the retina again and again, maybe the retina learns to slowly expand what it can see from starting with red and then slowly going along the color spectrum and only at the very end reaching the ability to actually see blue.
Now, to be clear, not everyone agreed with this Eurocentric view of human progression.
Especially the people who took Darwin's theory seriously once it came out, and the people who really started to think that way, they very quickly realized that, this story of gradual improvement in color vision, it didn't really make sense in this new framework of thinking about evolution, that it doesn't really work that way. And there were other things that seemed a little bit odd, like, for instance, okay, why is it that the Greeks paint with blue or, prize lapis lazuli, the blue gemstone, a lot, if they can't actually see it? Like, it just didn't really make sense. And so when people looked at it really critically, I think they realized that there seemed some pretty big holes in it. And also, there was a pretty obvious alternative explanation, right? Which was that they were always able to see these colors, they just didn't have a name for it. They didn't have a separate word for it.
Chapter 2: Perception versus Language. Now that there were two competing theories about color perception, all that was left to do was test them. One of the scientists who wanted to test these theories was a famous German physician named Rudolf Virchow. At the time, the Berlin Zoo had a human display, a Nubian tribe, which was as awful as it sounds.
And he went to them and he tested the color vision. He basically just checked whether they can distinguish, blue from green, for instance. And that way he found out that actually, yes, they don't have different words to describe these two colors, but they can easily distinguish them. There's nothing in their perception of color that is very different from the perception of color of a German at that time. And so that kind of evidence just started accumulating over time.
Hugo Magnus himself spearheaded a bigger study to get a definitive answer. He surveyed people around the world about the words they used to describe color.
In this example that Magnus describes from this pastoral tribe in Africa, they have all of these words to describe the different shades of the animals that they keep, because that is something that they need to talk about. But there's no point for them in being able to describe green and blue because that is just not something to talk about.
The tribe even found it funny that people would have words for the colors of things they regarded as unimportant. In most cases, they felt the object name was enough.
Because if a banana is always yellow, there's no need to say the color yellow, right? I mean, bananas can be green, but then you have ripe bananas and unripe, right?
In other words, if it had to do with their daily lives, it was important. But distinguishing between green and blue, when they already had words for grass and sky, not as important. And this was a pattern that emerged throughout the survey. Colors were named only when they were deemed necessary.
And once that evidence came in, it was just clear that, the words are lacking, but the perception isn't.
Shockingly, Magnus didn't greet this evidence with humility and a new understanding about his fellow humans. He dug his heels in deeper.
And this is something we see in science again and again, right? Like, people fall in love with their own ideas, and he did the right move in a way, you could argue, but then he was not able to actually take the result of that on and be like, yeah, okay, it's time to let go of this idea. And instead he defended it basically to the end.
Nevertheless, science moved on, and most people accepted the theory that it's language that develops, not our eyes. The question became,
is there an evolution in our perception over time as a species, or is it language that evolves?
That question is at the heart of something called linguistic relativity. It emerged in the 1920s and gave fuel to this growing debate. It was based on the work of linguists Edward Sapir and Benjamin Whorf. The so-called Sapir-Whorf hypothesis says that different languages represent reality in slightly different ways, and, in turn, shape how people see the world differently. Suffice it to say, it was a little bit controversial at first.
There are these ideas that are brought forward like, okay, here's a group of people that don't have a grammar form for the past. And then the argument is, well, they can't actually think about the past. They don't have language for it. And if you don't have language for it, you can't actually think those thoughts. Like, this is kind of the most extreme version of it that's out there.
Still, the concept not only became accepted, it was popular. And even though Sapir and Whorf never mentioned the color spectrum, people began to look at the age-old color perception debate through the lens of linguistic relativity.
And so the idea is that the color spectrum is, a physical thing. You have basically these different wavelengths and they correspond to different colors. But how a language carves up that color space is completely up to each language. So there is no set breaking points in the spectrum where you be like, okay, this is where one color ends and another color has to start. Different languages can just do whatever they want.
When you think through how this would actually work, it gets a little messy.
How would you even start to translate one language into another language if my yellow and one half of orange is one color for you, and then maybe 1/3 of orange is another color, and then orange, red, and green are another color for you? That's not really what we see in the world.
In the 1960s, two linguists named Paul Kay and Brent Berlin came of age when this theory reigned supreme. But when they were doing field work, Kay in Tahiti and Berlin in Mexico, they both came to the same conclusion, that this idea of arbitrarily dividing up the rainbow can't possibly be true. They found the same two surprising things in the Tahitian and Tseltal languages. One, their colors corresponded almost exactly to English. And two, the exception was that they had one word for blue and green, bleen, if you will. And so Kay and Berlin decided to investigate further. They surveyed people with 20 different mother tongues, and they looked in literature at 75 more. They wanted to figure out if there were any common colors in all of these languages.
They try to figure out, in a way, what are the atoms of color language? And they use this term basic color terms, which is really a color that is, it's not a compound, it's not sky blue or blood red, it's blue, red, and it's words that, that children already learn that they use to basically carve up the color space.
In English, there are 11 basic color terms: red, orange, yellow, green, blue, purple, pink, black, white, gray, and brown. Some languages have fewer, but their boundaries still fall in the same places as English. It's just there are fewer of them.
But the most interesting thing to them is that there seems to be a pattern in what words are missing.
Take languages that only have 3 color terms. Those tend to be black, white, and red. If a language has 5 color terms, they're often black, white, red, yellow, and green. Only when a language has these 5 colors first does it finally add blue.
And so they realize that there seems to be like this progression of color terms that seems to be very similar in different languages. And like in some way, this is similar to the idea that Magnus and others had about humans' perception evolving, only that now they do it with language.
So why in the world would a word for blue always come last? It's not because entire groups of people collectively could not see blue, and it's not because some people don't have any blue in their environments. We might not all live near the sea, but every single one of us lives under the sky. Being who we are, unprepared to leave any of those questions on the table, we turn to our dear colleague, Lisa Berry-Drago. She curated our museum's latest exhibit, Bold, Color from Test Tube to Textile. And of course, she also used to co-host this very podcast. Chapter 3, Fugitive Color.
Blue is really interesting because blue has been, I'm going to use the word fugitive. We've been chasing it.
For as long as humans have existed, the color blue has been all around us, or at least above us. And yet, we've only recently, in the scope of human history, been able to hold blue in our hands. That is, make blue dyes or pigments.
There's many things in nature where you can observe the optical phenomena. The sky, the water looks blue, but it doesn't make blue. Because things that have chemical properties to create blue are different from things that have optical properties to look blue. If it's something that you can see and you cannot capture.
That's the difference, right?
And the capturing is what makes the difference in terms of naming a color. If identifying a color doesn't have a huge impact on your daily life, then you probably don't need a name for it. It doesn't need to be the blue sea. For most day-to-day life, just sea will suffice. Maybe you need a word to indicate that it's too choppy, but a color doesn't really matter. Once you can turn other stuff blue, though, like a piece of cloth or a canvas to paint that sea, then having the word blue becomes important. And green has a similar story.
What color is beautiful, bold, green grass that stains your hands and your clothes green? What color does it resolve to when it dries?
Yellow. You told us this, right?
Yellow, brown. It's because the color of grass is chlorophyll. Chlorophyll cannot be turned into a dye or pigment. Chlorophyll is an organic compound that loses its color at cell death, basically. You know, like it doesn't stay. There are so many things in nature that have color that you cannot extract the color from. That is a very specific subset of the natural world, things that you can actually capture the color from.
The earliest humans were able to capture black, white, and red. Remember, Paul Kay and Brent Berlin found those were the colors that always showed up in languages with only 3 color terms.
That makes perfect sense to me if you look at, like, cave painting. What pigments do cave painters have on hand? They have carbon black from burnt bones. They have blood, which is red when applied and then becomes a rusty brown, you know, when as it oxidizes. So they go to the next thing. They go to berries, or they go to bugs. The Kermes insect is around in the Middle East. Cochineal is around in the Americas. And very early on, people are like, when I crush this, it stains my hands for days. Anything that stains your hands for days, not for hours, but for days, is probably a good source of dye.
So when you're looking around for things to capture red, you've got options. Berries, flowers, even the earth itself.
We have ochre-containing earths. Heavily iron-containing earths have a lot of redness to them. So there's lots of sources very early on. And I mean, I don't even mean 6,000 years ago. I mean 25,000 years ago. Right. Do you know what I mean?
But like we said earlier, nearly everything you can think of in nature that looks blue doesn't make blue. Like blueberries.
If you try to dye something with blueberries, you end up with a slightly purplish red. They don't make blue.
Or bluebirds.
Bluebirds don't make blue. You can't, like, boil a blue bird and get blue dye.
It's not until a mere 6,000 years ago that we finally captured blue.
Indigo. Indigo is the most notable, most important one. But there's almost no other sources of blue dye, blue color, until you're getting up to the sort of pre-industrial age. So really, in the ancient world, our sources for blue are indigo, largely.
If you've ever worn blue jeans, you're familiar with indigo. These days, we use synthetic dye to get that deep, rich blue color. But those original Levi's used the real thing. And what's the real thing, you might ask? A plant. Originally from India. And back in the 18th century, indigo played almost as big a role in colonization as cotton did in slavery.
Indigo and cotton. People think of cotton. They don't think of indigo. Indigo and cotton. Cotton and indigo were 2 of the foundational cash crops of the South. There's also tobacco. There's also rice. We forget about how much rice we've grown in America. But tobacco, rice, cotton, indigo is a missing piece of that puzzle.
Once people figured out that indigo, along with its cousin plant woad, which grew in Europe, produced a lasting blue color, they went crazy for it. And one of the reasons it came so much later than, say, red dye was because indigo and woad plants were way less obvious sources of color.
They're both kind of unlikely looking shrubs.
This is Victoria Fenley, the author of Color, A Natural History of the Palette.
I thought that there would be something blue about indigo. I had imagined so much about these indigo shrubs, but anyway, none of them were true.
Indigo is an unremarkable looking plant. Its stems have rows of small green leaves and these tiny blooms of pink or purple flowers. But it's the leaves, the green leaves, that create the deep blue dye.
and you've got to really work them to make them into a blue dye.
The basic process involved fermenting leaves, sort of like brewing beer, which resulted in a sludgy mess that had to sit in a vat for months. It sounds simple enough, but in reality, there were a lot of complications.
Think about that process for a second and think about how many factors can impact the color that you actually get. So the soil that the leaves are grown in, because this is an organic product, right? Time of year that they're grown, the amount of sun that they're getting, how developed the plants are, the way that they're processed, the way that they're dried. Are they dried quickly? Are they dried slowly?
And then there's the temperature of the water. Are you controlling it properly? And what type of material is your vat made of? Is it copper, stone? All of this makes an impact.
There are so many different kinds of chemical interactions that you can have in natural dyeing, from the plant in the ground, to the dye vat, is an enormously complicated process, even if that happens invisibly. And when we say we have indigo textiles from 6,000 years ago, we don't necessarily have like the rich, deep, fermented indigo colors. We have those lighter blues and greens that come from using it in a more raw state. So we don't have the deep, beautiful indigo blue that you think of as the classic indigo, the rich, dark indigo color. We don't have that until fairly recent in human history.
For thousands of years, indigo/woad was the way to color something blue, as long as you were coloring a fabric or skin, like early British warriors used to do. But if you wanted to color something like a wall or a canvas, you would need a pigment, not a dye. And this, a few thousand years after indigo dye, is where the ultramarine pigment comes in. Cave paintings in Afghanistan, traced to around 700 or 800 AD, feature a pigment called ultramarine. It's a beautiful, brilliant blue that comes from the stones mined nearby.
So it's a semi-precious stone that you probably know about. It's lapis lazuli. And I'm going to be very frustrating for people listening to this podcast, because I'm going to pick up a lump of lapis lazuli as big as, I'd say, my hand. And it's got some very dark, beautiful, almost violet blue bits and some quite sort of cloudy blue bits. And then it's got some really kind of rocky grey bits.
And running through this is a little strip of pyrite, or fool's gold. It makes the whole thing sort of sparkle. And this stone is one of the very rare things in nature that is blue and makes blue. But like indigo dye production, it took an incredible amount of work to turn this rock into a powdered pigment fit for a Renaissance painter. First, you had to get the stone out of the mountain.
They would light a fire under the tunnel, and then the fire would heat the rock above it, and then they would throw this ice water from the river below, and then that would crack, and then they could prise it off.
But you still had a ways to go to get the pigment out of this rock.
You would, first of all, bash it. you'd smash it and bash it into the tiniest powder that you can possibly make it, and then you'd smash it into more powder. But that's not good enough, because that still has got a lot of imperfections. So then you'd mix it with resin and wax and glue and honey sometimes.
And you'd knead this lump together, like a baker would knead dough. Or more likely, you'd get someone else to do this part for you.
Somebody kind of strong would have to knead it for like 3 days.
After that, you'd add water, the right amount of water, which would also turn blue, and then you'd take the dough out and let it rest in the sun. And when the water evaporates, you'd have just a tiny bit of powder at the bottom of the bowl, and that's your ultramarine pigment. And then you'd do the whole thing over again.
And that would be the second pressing, and that wouldn't be quite as good, etc. And then you'd keep on going while there was still blue, because this was, really expensive. It was rare, but also so far it had come.
By the end of the Middle Ages, both ultramarine pigment and the lapis lazuli itself were traveling long distances from Afghanistan to Europe.
It was so exotic. I always thought that ultramarine meant sea color, but actually it doesn't. It means beyond the seas, ultramarine.
In Europe, the most famous painters of the time, of all time really, use this precious pigment in their masterpieces. Vermeer's Girl with a Pearl Earring, her head wrap is ultramarine. The sky of the Sistine Chapel, ultramarine. But one of the best examples of the pigment is actually where it's not. If you go to the National Gallery of London and look at Michelangelo's 1501 painting of the Entombment, you'll see that the bottom right-hand corner isn't finished.
That was going to be the Virgin Mary, who wears blue in paintings of that time, and most paintings, in fact, because it was the most valuable paint. It was so expensive that Michelangelo couldn't afford it himself. Gold and blue, ultramarine blue, were delivered by the patron who had paid for the painting, because an artist couldn't be expected to have it hanging around. So he was probably waiting for the blue. And then, well, he was invited to go to Florence and make his David. And he kind of abandoned it, and it was never finished.
Instead of Mary wearing the brilliant blue, she's not in the painting at all. It's a testament to how much we prized this color. I mean, think about it. To make blue, to capture it, not just see it, you could either ferment the leaves of a plant that in no way offers any hints that it's blue and not green, all the while carefully studying the soil and the water temperature and the metal your pot is made out of. Or you could travel to Afghanistan, which might as well have been on another planet, it was so far away, blast some rocks out of a mine, and process the powder you've ground for days on end, all to get maybe a tablespoon of pigment. On the other hand, if you wanted the color red, you just had to find the right berry or bug and squish it. When you do all of that for a color, you're definitely going to start having a name for it. Which brings up something Victoria said that we found surprising. In Afghanistan, the place where everyone was getting all that lapis lazuli and ultramarine pigment, they have some surprising ways of describing the different types of lapis lazuli.
They said that there were three main colours. So one was called rang-i-ob, which means the colour of water. Ob is water. And that was normal blue, right? Normal, everyday pigment. And then there was rangi-sabz, which is like vegetable, like greens. And then there was the best one, and that was called surpar, which is red feather.
That's right. The blue stone that literally helped put the word blue on the map is described by the people closest to it as red. But Victoria tells us there's a good and slightly poetic reason for this.
It's the very hottest bit of the flame. And what colour is the very hottest bit of the flame? It's blue. It's violet blue. So I'm going to ask you to either remember or just look at a candle or a gas fire flame or something. Where it's the best colour blue, that's the colour of ultramarine.
We started this story talking about William Gladstone and how he believed the ancient Greeks couldn't see the color blue, that there was essentially something wrong with their eyes because they never used the word blue. And I'll admit, we were a little judgy towards him. But when I think about it, we were kind of doing the same thing to each other when we were arguing about the dress. So we decided to ask Kai about it.
That's not on our list of questions, but we should ask about it.
Yeah.
What do you know? You know what we're talking about, right?
Yeah.
The dress?
Yeah.
How did you see it?
Yeah.
Oh my God, I have to look back at it. I think I saw it as, that's a good question. I think I saw it as blue and black, and others saw it as gold and what was it? Gold and white.
Alexis,
yeah,
that's right.
And I mean, there's all of these theories about it, right? But the reason, like you say, I think the reason it blew up was this kind of almost metaphysical disorientation of how can it be that you look at this and you see something that is different from what I see? And so it was just really shocking to a lot of people that they would not be able to agree with their spouse or their best friend about what color this dress is. Yeah. It's just like this moment where the whole world, like for a moment, like realizes, oh, wait a minute, we do perceive the world through filters. I mean, we all know that, but it was just like, right there in your face.
The filters Kai's talking about have to do with the assumptions we all make all of the time. When we look at the dress, we make immediate assumptions about the light. Now, the picture itself is no photographic masterpiece. It's overexposed, for one thing, which means you can't really tell what kind of lighting there is. So, we have to decide if the dress is in shadow or in artificial light. If we think it's in shadow, then we subtract blue light. If we think it's artificial lighting, we subtract yellow light, making the dress appear white and gold or blue and black, respectively.
Well, we relived it recently.
Yeah.
And 3 out of 4 of us saw white and gold, and Alexis saw blue and black, and we all of our brains exploded.
Yeah.
Because I was just like, what else are you seeing? You're like walking around in an upside down world.
There's something so fundamental about it that we expect it to just be the same for everybody. And I think that's where this original kind of shock for like Gladstone and others comes from. It's like, wait a minute, like how can somebody see the Greek blue sky and not describe it in, blue terms? It feels like something that should be very easy and obvious, but it really isn't. It's when you get into it, it just eludes you. And I think there's something about that really fascinates also scientists, because scientists love getting to like the ultimate answer in a way. And there's something about color that never allows you to really get to that ultimate answer.
But of course, that won't stop them from trying. An NYU neuroscientist named Pascal Wallish was fascinated by the dress fiasco and made a study out of it. He found that people who are night owls, like myself, are more likely to see the dress as blue and black, and that people who are morning larks, like Mariel and Sarah, are more likely to see it as gold and white, all because of the lighting we're more accustomed to. Turns out we bring our personal experiences to everything, including color. Now, in case you're worried, the Distillations team continues. We're still friends, still hunting down answers about fascinating things in the history of science, and still happy to sit in a space where the answers to those questions might be complicated.
One of the things that I'm realizing is that our world would be so much better off if people had a little bit more of that, let me call it epistemic uncertainty. Just this feeling that, oh, wow, okay, you can look at this world and like see really different things. And but we're talking about the same object. And, maybe the filters I have really have much more of an influence. So it does all tie back into like these same themes for me that I keep coming back to, which is really, how do we relate to the world? How do we relate to each other? And how much humility do we bring to that? And it just doesn't feel like we bring the humility that, an episode like that dress should have taught us to have.
Distillations is produced by the Science History Institute. Our executive producer is Mariel Carr. Our producer is Rigoberto Hernandez. And our associate producer is Sarah Kaplan. This episode was reported by myself and Mariel Carr and mixed by Jonathan Pfeffer, who also composed the theme music. This episode was inspired by our museum exhibit, Bold, Color from Test Tube to Textile. You can learn more at sciencehistory.org/bold. You can find all our podcasts as well as videos and articles at sciencehistory.org/stories. And you can follow the Science History Institute on Facebook, Twitter, and Instagram for news about our podcast and everything else going on in our free museum and library. For Distillations, I'm Alexis Petrick. Thanks for listening.